Dear students, good morning, Jai Hind. Myself Dr. Pankaj Goel, working as an assistant professor in the Department of Electronics and Communication Engineering at Akgec. Today we will discuss a very important topic, ion implantation working principle and annealing process, from the subject VLSI technology. The topics that we are going to cover in this presentation are introduction, diffusion versus ion implantation schematic and working principle, stopping mechanisms, damage and annealing, and references. Okay. Now, first of all, let us understand what is ion implantation process. So, ion implantation is a low temperature technique for the introduction of impurities into the semiconductors, and it offers more controlled doping as compared to diffusion process. As we know that in case of VLSI fabrication on a intrinsic semiconductor, we have to diffuse or we have to dope the semiconductor with different type of dopants or impurities, be it p-type impurities or n-type impurities. Now, for this doping, broadly there are two type of processes which are known as diffusion and ion implantation. So, ion implantation process as compared to diffusion is more controlled, more precise, and it is a low temperature process, which is again a very important benefit of it. In diffusion, the surface concentration is always going to be the highest concentration. As we know that in case of diffusion, the flow of dopants is from higher concentration region to lower concentration region. So, because the dopants flow into the wafer from the surface, so surface is always going to have the highest concentration. So, because there is a concentration gradient between the surface and the bulk of the wafer, so dopants move from surface to the bulk of the wafer, but surface concentration is always going to be the highest concentration. But it is not the case in case of ion implantation. In case of ion implantation, we can decide at what depth the concentration of the dopants. At different distances from the surface, the dopant concentration can be controlled, can be varied in ion implantation process. Whereas in case of diffusion, we know that the surface concentration is always the highest. So, this limitation is removed in case of ion implantation process. Graphically, we can see that ion implantation is a more precise, more controlled process. Here we can see this is our ion implantation doping. Here the dopants are bombarded onto the wafer and the dopants move vertically inside the bulk of the wafer. They are not moving laterally where they are not desired. In this region, below this region, dopants should not go. Okay, and it is actually happening here in case of ion implantation. The dopants are not moving laterally below this layer, PR layer, photoresist layer. Whereas in case of diffusion, we can see when due to concentration gradient, dopants move from surface to the bulk of the wafer, the dopants move vertically as well as horizontally, laterally. So, this is undesired area. We do not want dopant here in this area beneath the silicon dioxide and PR photoresist layer. So this is undesired. So in case of diffusion, it is not very well controlled process, but ion implantation is a very well controlled process. This is controlled process. Now let us discuss the schematic diagram of a ion implantation system. Here we can see, here we have a ion source. From here the ion source provides the desired dopant ions. These desired dopant ions move inside the magnet analyzer. What this magnet analyzer do? It only pass the desired dopants and the undesired dopants, undesired impurities. There may be undesired impurities which may be there because of the various components and the chamber material, because when we are generating the dopant ions from this ion source, at the same time, due to ejection of impurities from the components and the chamber, undesired impurities also get added into the desired dopants. So the purpose of magnet analyzer is to pass only the desired impurities, desired dopants, and stop the undesired dopants, undesired impurities. Now, so these desired dopants pass through the magnet analyzer, and then there is a ion selection aperture which provide a well collimated beam. Here next we can see here. Beam collimator. So this aperture provide a well collimated beam. Now after this we have an acceleration tube. The purpose of this acceleration tube is to provide the sufficient energy to the beam, because the energy that is provided to the beam decide at what depth the dopants goes into the wafer. Higher the energy, more the depth into which the dopant beam can penetrate into the wafer. Lower the energy, lower the distance they travel inside the wafer. Okay, then we have the lens and the deflection plates, and here it is the wafer, and this is the wafer holder. So these dopant ion beam is bombarded onto this wafer surface. Let us see some more description of ion implantation process. During ion implantation, dopants are ionized, accelerated and directed at a silicon wafer or silicon substrate. Then when these dopant ions enter the crystal lattice, they collide with the silicon atoms and gradually lose energy, finally coming to rest at some depth within the lattice. The average depth can be controlled by adjusting the acceleration energy, and this acceleration energy is provided by the acceleration tube. Also, the dopant dose can be controlled by monitoring the ion current during the implantation process. Now, the basic requirement for an ion implantation system is to deliver a beam of ions of a particular type and energy to the surface of a silicon wafer the dopant source is a compound of the dopant material and is usually a gaseous compound of the dopant. Here in this figure we can see that there is a high energy, high voltage system the gas source that is used may contain a gas such as BF3. It goes into the ion source where a heated filament causes the molecules to break up into the charged fragments. Now, this ion plasma contains the desired ion together with many other species from other fragments and contamination. So, these are the undesired impurities, okay, with many other fragments and contamination. This is undesired impurities. The extraction voltage of around 20 kilovolt cause the charged ions to move out of the ion source into the magnet analyzer. The pressure in the remainder of the machine is kept below 10 raised to the power -6 torr to minimize the ion scattering by gas molecules, because if it is not a vacuum, then what happens? The ions, when they travel, they get scattered. Okay, so to stop that deflection or scattering of the dopant ions, the pressure is kept at very low level, that is around 10 raised to the power -6 torr. And the magnet field of the analyzer is chosen such that only the ions with desired charge to mass ratio can travel without being blocked by the analyzer walls. Now, surviving ions continue to the acceleration tube. The aperture ensures that the beam is well collimated, and then we use the electrostatic deflection plates. These electrostatic deflection plates are used to scan the beam over the surface of the wafer. Okay, with the help of deflection plates, the ion beam is moving onto the wafer surface. It covers the whole wafer surface wherever the dopants are required to be introduced into the wafer, and the beam is deflected with the help of these deflection plates. Here we can see these deflection plates, x axis and y axis direction is decided by this x scan and y scan deflection plates. Okay. A typical commercial ion implanter system specifications are given here. Here we can see it is around 6 meter long, 3 meter wide, 2 meter high, and it consumes around 45 kilowatt of power and can process approximately 200 wafers per hour with a dose of 10 raised to the power 15 ions per square centimeter, 100 wafers. So, this is a specification of a typical commercial ion implanter system which is used in the industry. Now, let us discuss the stopping mechanism. As we know that the dopant beam is bombarded onto the wafer surface now, and after traveling some distance inside the wafer, the dopants come to rest. Now, how they are stopped inside the wafer surface? For that, there are two stopping mechanisms. One is known as nuclear stopping and the other is known as electronic stopping. Okay. Graphically, we can see in case of nuclear stopping, the dopant ions collided with the host silicon lattice atom and lose energy in the process. Passes through the outer shell of the atom, where the electrons which are present in the outer shell or valence shell, because these outer shell electrons need very small energy to come out of that valence shell and get free. So, when dopant ions do not collide head on with the silicon atoms, but they travel through the valence shell of the atom, then they eject these electrons and make them free, and in the process lose very small amount of energy. So, in case of electronic stopping mechanism, our dopant ions travel much far distance as compared to nuclear stopping. In case of nuclear stopping, the distance traveled by the dopant ions is less. Here we can see, if we have lighter ions, then they are more in electronic stopping. If they have heavier ions, then it is more of nuclear stopping mechanism. If there is nuclear stopping, this is the curve it follows. So, the distance travelled is very less, but if it is electronic stopping, the distance travelled is much larger. Now, as we just discussed that in case of ion implantation, beam of dopants is bombarded onto the wafer surface. In this process, what happens? The surface of the wafer get damaged. Silicon atoms are at equal distance from each other, but after implantation, what happens? The structure get damaged. They are not at equal distance from each other, and also the dopant atoms get introduced into the lattice. So, these dark circles represent the dopant atoms. And this structure is damaged structure, we can see here. So, after ion implantation process is done, we need to correct this damaged structure. We need to heal this damaged structure by a process which is known as annealing process. Annealing is the heat treatment process which is used to restore the disordered semiconductor wafers to single crystal structure. Okay, because we know that when dopants are bombarded onto the silicon wafer, it get damaged. So, we say the structure is disordered. So, this disordered structure need to be corrected. It need to be restored into its original form. Original form is known as single crystal structure. Now, what happens is, when the dopants are bombarded onto the wafer, they may not be at a regular lattice location. They may be at the interstitial site. So, if our dopant is at interstitial site, it is not electrically active. The dopant atom, in case of silicon structure, to be activated as donor or acceptor, it must be bonded with 4 silicon atoms. It must be bonded with 4 silicon atoms. Okay, and that will happen only when the dopant atom is at the substitutional site, not at the interstitial site, minimize the diffusion. We know that in case of diffusion, what happens? Due to concentration gradient, the dopant move from one region to another region. Now, and we know that diffusion is a high temperature process, ion implantation is a low temperature process. So, diffusion is a high temperature process and annealing is also a high temperature process. So, what happens when we do annealing? Diffusion also happens, and this is undesired diffusion. We do not want this diffusion to happen, but because it is a high temperature process, diffusion happens. And if we do annealing to restore the crystal structure, we have to take into consideration the effect of diffusion. Our objective should be to minimize the diffusion when annealing is going on. So, for that what we do? We do RTA, rapid thermal annealing. So, RTA is a very high speed annealing process that in a few seconds we raise the temperature to heal the structure, to restore the structure, and then the temperature is lowered, so that diffusion does not happen. If for a long time we are in a high temperature state, the dopants will move from one region to another region. So, to avoid that, we prefer to use RTA technique, rapid thermal annealing, which is of the order of seconds. So, here graphically we can see the thermal annealing. Here initially the structure is damaged structure, which is disordered or amorphous. Damaged, disordered or amorphous, one and the same thing. So, this is the disordered structure or amorphous structure. Now, when we are starting our annealing process, what we see gradually the structure is getting in ordered state. First question is, what is meant by annealing? This may be asked in 2 marks question. The second is, explain ion implantation process, its advantages and disadvantages. Third is, what is ion implantation? Why is ion implantation preferred over diffusion for impurity doping? Explain briefly the ion implantation technique with labeled sketch. And there is another question, explain the ion implantation technique with labeled sketch, also mention its advantages and disadvantages. These are the questions which have been previously asked in the university exams. The book that I have referred for this particular topic is VLSI Technology by SMZ from McGraw-Hill Education. For more detailed study, you may refer this book.